Well, to continue with our discussions on partially miscible systems, we had already discussed the phase diagram for miscible systems. We also tried to find out why certain systems are miscible under certain conditions and they are immiscible under certain conditions. But I would just like to elaborate slightly on this. Particularly, I would like to discuss the effect of pressure on the zone of or the tendency of miscibility and immiscibility. Just like I had discussed in the previous class, two components are going to mix with one another provided this leads to a lowering of the Gibbs free energy of the system. If on mixing the Gibbs free energy of the system increases, definitely the components will prefer to stay separated, and only if the Gibbs free energy decreases they are going to form a miscible solution. Right. Now, what decides whether the Gibbs free energy is going to increase or decrease when the two components are brought close, or rather when the two components are contacted with one another. If you recall, what did we had already discussed that del G, say del G mixture del P at constant T and X. What was this? This was related to the volume of mixing, if you remember. Okay. And this is the main equation which tells you that what is going to happen when the two components are brought close to one another. Now, two components will be mixing, as I have already mentioned, provided delta G mix is less than 0 and del 2 G mix del X 2 at constant temperature and pressure is greater than 0 for all x. Only if this happens, then only the two liquids are going to be miscible in all proportions. Now, we know that delta G mix, it is a function of pressure, and therefore, when we find that while increase in pressure, it may lead to miscibility of the two components, just like I had shown in this particular case, it may also lead to immiscibility of the two components. So, very naturally from this equation it is evident that that should depend upon the sign of V mix. Suppose we bring two components and we mix them together and we find that V mix is actually greater than 0, then we know that when the two components are mixed and the variation of the G mixture with pressure is going to be positive. So, at higher pressure we are going to get a positive value or a higher value of G mix. So, naturally when we are going at higher pressure, a situation is going to arise when initially at a lower pressure it had formed, initially at a lower pressure it was completely mixed, and when we increase the pressure, when delta V mix is greater than 0, this is the mixture delta V and this is also G mixture. So, therefore, when delta V mix is greater than 0, when we go for a higher pressure, we find that delta G mix is actually increased and there is a hump, as a result of which partial miscibility results, and in this particular composition range given by x1 prime and x1 double prime, the two components separate out into two liquid phases while they are miscible beyond x1 prime and beyond x1 double prime. Similarly, suppose we have one particular system which is immiscible at low pressures. The curve which, rather the system which is given by the curve A, denoting that delta G mixture as a function of the composition. From this particular curve we find that there is partial miscibility between x1 prime and x1 double prime under the condition denoted by curve A. And we know that for this case delta V mixture is negative, it is less than 0. Now, for such a case, suppose we increase the pressure. What happens? Delta G mixture reduces, and as a result we find that the solution or the system, it was partially miscible at lower pressure, but it becomes completely miscible at higher pressures. So, therefore, from such simple variations we can very well understand that the qualitative effect of pressure on phase stability of binary liquid mixture It depends upon the magnitude as well as the sign of the volume change of mixing. And therefore, if we really want to perform quantitative calculations at some fixed temperature, we need to have information of the variation of delta V mixture with Xp. We need to have this particular information along with delta G mixture as a function of X at a single pressure. Only if we have this data, we can find out that under what conditions the two components will be mixing, under what components the two components will not be mixing, they will be forming immiscible systems, and if by increase of pressure we would land up into a miscible system or an immiscible system. It all depends upon the sign and magnitude of the volume change of mixing of the two liquids. Now, let us go to the extreme of this particular situation. We have been dealing with partially miscible systems, we have been dealing with completely miscible systems. Now, let us go to completely immiscible systems. Again, under this condition, I would like to remind you that in reality it is very difficult to have a completely immiscible system. Such systems, well, before that I would just like to mention that this is the corresponding PXY diagram corresponding to the TXY diagram here. It is interesting to note that while in the TXY diagram we found that the solubilities, they were increasing with pressure. In this particular case, the lines are more or less vertical, which indicates that pressure insensitivity of liquid solubility, which we already know. Well, now to continue with our discussions with completely immiscible systems. Again, as I was repeating at that time, usually completely immiscible systems are not there in practice, but they can be approached by several systems. So, what should be the typical TXY and PXY diagram in this condition? Again, when there are completely immiscible systems, we know that for 3 phases to coexist, F equals to 1. So, therefore, if we are drawing PXY at a constant temperature or TXY at a constant pressure, then there will be just one point where the 3 phases can coexist, just like we have discussed in partially miscible systems. What is this point? If you observe these two curves, this point is given by the point B. Only here we have the 3 phases existing. This is denoted, as I have said, by a 3 phase equilibrium temperature T star and a 3 phase equilibrium pressure P star, right. Now, other than this, what happens to the other regions? Suppose we are operating at a temperature lower than the 3 phase equilibrium temperature. We do not have any vapor under this condition. We have 2 completely immiscible liquid systems. If we are operating at temperatures above T star, we can have either a vapor phase, or we can have the vapor in equilibrium with one of the liquids, pure liquid, mind it, it is not a liquid solution. In this case, L1 means pure liquid L1, unlike the previous case where for partially miscible systems I had mentioned that L1 is a solution of 2 in 1. In this case, L1 refers to pure liquid 1, or in other words, depending upon the overall composition, we can have a vapor phase in equilibrium with pure liquid L2. Now, in this case also we find that suppose we start from state 1 and we start cooling the liquid at cooling the vapor at constant temperature. What happens? Cooling continues, and since it is a constant pressure cooling, so naturally it follows the vertical line, say 1, 2, 3. As cooling proceeds, the vapor reaches the point 2. At 2, the first drop of liquid appears. What is this liquid? It is pure liquid L1, mind it, right. We continue the cooling process. We get greater and greater proportion of liquid L1, and the vapor composition, it is given in this case by Y5. We keep on continuing the cooling process further. We find that the vapor composition varies along path CB, and we get more and more of liquid L1, and finally when we have touched this particular horizontal line, the entire vapor has condensed to give us liquid L1, and the remaining portion is L2, which forms a separate layer. It does not mix with L1. On the contrary, if we have a vapor of overall composition say Y7 and we start cooling it, we find that in this case also it follows a vertical line, naturally constant pressure cooling, and when it reaches point 8, the first due of liquid which appears is pure liquid L2. And if we continue the cooling process, we get greater and greater proportion of liquid L2, and the vapor composition, it keeps on decreasing along the path AB. And finally, when we continue the cooling process and reach this particular horizontal line, say this horizontal line is JK. So, when it reaches this particular horizontal line, we find that the entire vapor has disappeared and we get pure liquid L2, and definitely whatever component 1 was there in the vapor, that condenses and separates out into a different liquid L1. And suppose we start, rather we have the vapor of composition say say YB, and we continue the cooling process. We find that we have only a single phase vapor region as long as the cooling continues. Then suddenly at the 3 phase equilibrium temperature, entire vapor disappears and 2 liquids are formed. The proportion of the 2 liquids are same as the vapor or the same as the proportion of the 2 components in the vapor phase, right. So, therefore, this is the phase diagram, and since this is comparatively simple, we can develop the mathematical equations which will be required in order to construct this particular phase diagram. What are the things that we need? We need to first locate the point B, and then we need to find out the locus of curves BC, the locus of curves AB, and the horizontal line. We assume for a time being that we are dealing with low pressure systems. For low pressure systems, it is the standard VLE relation which we have written n number of times in our entire course. It is given by gamma I xi, the standard relation, this is equals to yip. Now, if we apply this relation to the point B, say at point B, what is there? We find at point B, vapor is in equilibrium with liquid L1 and vapor is in equilibrium with liquid L2. So, there will be 2 equilibrium relations. For the first case, what will we have? For the first case, it should be gamma 1 x1 p1 saturated will be equal to y1 p. And again we remember that in this case x1 is equal to 1, we have pure liquid. Since x1 equals to 1, naturally gamma 1 will also be equal to 1. So, at point B, what is y1 equals to? It is p1 saturated by p. Similarly, at point B, the equilibrium relationship governing the equilibrium of vapor and liquid L2, this is again going to be the same relationship with the same considerations, which gives y2 is going to be p2 saturated by p. And therefore, once we know that the y1 star and y2 star at the 3 phase equilibrium temperature, we should be able to find out the p star under this condition, which is nothing but equal to p1 saturated plus p2 saturated. And we observe one more interesting thing. We find that at any particular specified temperature, at any particular specified pressure, say for example, this phase diagram is drawn at a constant pressure. For such a case, if 2 immiscible liquid phases are in equilibrium with the vapor phase, we find that the 3 phase equilibrium temperature will always be less than the saturation temperature of either liquids at that pressure. Is it clear? We will always find that Tb will be lower than the equilibrium saturation temperature of liquid L2 and the equilibrium saturation temperature of liquid L1. This is always going to happen. So, therefore, under this condition we have found out what is the composition of y 1 star, we have found out the composition of y 2 star, and we have also found out what should be P star under this condition. And this P 1 sat and P 2 saturated, they both of them they are functions of T star. So, therefore, we are in a position to locate point B. Now, suppose I would like to concentrate on this particular region. In this particular region L 1 plus V, what is the we know that it is pure liquid L 1. For this region we just need to know the locus or of this particular curve, and we need to know the locus of this curve. Along this curve we know y 1 is in equilibrium with pure liquid L 1. So, therefore, for this curve can we not write down that again from the same equation these two cancel out, can we not write down that along curve CB y 1 P is equals to P 1 saturated, or in other words for this particular curve y 1 will be given by P 1 saturated by P and y 2 will be given by 1 minus P 1 saturated by P, or in other words P minus P 1 saturated by P. Agreed? And what about curve AB? For this case again P 2 saturated should be equal to y 2 P, from where we know y 2 should be equal to P 2 saturated by P and y 1 should be P minus P 2 saturated by P. So, therefore, once we can locate the 3 phase equilibrium point, the P star, we can locate the T star, because under that particular T star the P 1 saturated and the P 2 saturated that we get and the y 1 star and y 2 star that we get, these two y's sigma yi star should be equal to 1. So, therefore, we can locate P star from the saturation pressures, we can locate or rather we can estimate the mole fractions of the two phases, and once we find that the mole fractions sum up to 1, we know that our assumed temperature also corresponds to the 3 phase equilibrium temperature. So, therefore, from this we can find out or locate the point B. Once we can locate the point B, we can very easily find out the slopes of CB and AB. The slope of CB or the composition variation along CB is given by this particular equation, and the composition variation along AB is given by this particular equation. So, with these we can it's quite easy to construct the TXY and the PXY diagrams for completely miscible systems. Well, this completes the vapor liquid equilibrium discussions of different systems. We have considered completely miscible, partially miscible and completely miscible systems. We have among completely miscible systems, we have considered ideal solutions and non-ideal solutions, and we have also tried to find out how from pure component properties we shall be in a position to find out the properties of the solutions and for both the liquid phase as well as the vapor phase. In the next class, I will be giving you a short discussion on equilibrium studies or equilibrium considerations for other mass transfer processes. Since distillation is one of the most important mass transfer process, so therefore, thermodynamics primarily deals with the vapor liquid equilibrium of the vapor liquid equilibrium of different systems. But definitely apart from distillation, we also have to deal with other processes like absorption, adsorption, etc. As you read these processes, you will be exposed into greater details regarding the equilibrium equations or the equilibrium considerations for this process. But here I would just like to present a very brief discussion of the equilibrium considerations for other processes. So, we do that in the next class, and that is going to end up our course on phase equilibrium thermodynamics.